Okay, the most important piece of mathematical structure for atomic and molecular physics is this representation of a irreducible representation set for the rotation or SU2 groups. So that's what we're going to spend the time today is looking at it from a lot of different ways. First step is to use the formulas that we've already done here. This is just review number 3 page. We'll look very quickly at review 1 and 2 as well. That set us up to do that in an elegant fashion. The Schwinger finesse is just one of those things that helps us with this, and there are some others that I want you to be aware of. And we'll need them as we go to bigger and bigger molecules, so it's really important to take a look at this. So that will be a good part of our lecture today, is first of all finding ways to make and evaluate the representations, but then I want to point out right now on the front page here, the applications of these things are a lot more than most people think of. First of all, we're going to be able to get the spherical harmonics just for reading off with all of their phases and normalizations in place. And we'll show examples of that for angular momentum 1 and 2, and maybe a little bit higher as well. They are also used, and this is, people almost always know about this, these are the things that transform the spherical harmonics. Well, they transform because they're made of them. That's really what it's doing. We need to see the beginning of the projector analysis that we'll use for all of our groups, and particularly for finite groups. And the transformation that they accomplish of this, of the various wave functions is very important. So we're going to see all of the things that involve the angular momentum cone uncertainty relations, which we'll show very early in this as we begin this discussion. So I'm taking this one back here to review 1 just to make sure that we are on the same page. Our first example of a projection operator that wasn't idempotent was this guy right here. And of course there are 3 others, 2 of which are diagonal and 2 of which, like this one, are just in the 1-2 position. Those projection operators would be written in Dirac notation like this, but that Dirac notation is replaced in order to accomplish what we're going to do here, and that is build up an infinite set of irreducible representations of rotations. And that begins with these creation-destruction operators that are, at least at first, directly analogous to, for example, this one here, 1-2, is really the same as that if you're only going to work with spin and half 2x2 matrices. But this is designed to go to the stars, so to speak, and get all of the irreducible representations of all angular momenta. And a lot of what we're going to talk about today are ways to understand and look at and simplify high angular momentum. That is our trademark, as a matter of fact. This was something that hadn't been done until this came along. So the commutation relations and all of that are part of our basic Lie algebra that we're doing here in order to build up, using harmonic oscillator creation operators, what we need to do angular momentum theory. And the idea of having a quantum number from a 2-dimensional oscillator, 1 dimension, 2 dimension, equal to the sum of an angular momentum total and a z component of angular momentum, or the difference, is really important, and will help us a lot here. So the eigenvalues that we get for our oscillator in 2 dimensions, the frequency times the number of quanta plus, and then in the 2nd dimension, the frequency times the number of quanta, and obviously that generalizes to higher dimensional harmonic oscillators. But in any case, the replacement of the numbers themselves by J plus M and J minus M, that's what we'll do that's part of what we'll do shortly. And also the raising and lowering operators have the usual square roots of n plus or minus 1, and then same thing for the second dimension, depending on what it is that you have here. And then these are the angular momentum matrix elements, just identical to these, except for replacing that number n by j plus or minus m. So that's a key. And we showed the generators, the equivalents of the spinners, as the raising and lowering operators, and then the z component, which is diagonal, for the vector. That's j equal 1. We'll be very quick. That's the first one we're going to do a picture of, and we're going to look at the wave function and see what their properties are. And then j equals 3/2 was next. We'll skip that one today. We're mostly going to look at the integral angular momentum stuff that's allowed for quantum rotors, and that's what we need to get finished in this week. We'd like to look at as much as we can of that. Now, the angular momentum magnitude is the weird one. Remember, we looked on the first day at some spectra, and I said j squared isn't good enough to work with the magnitude squared. You've got to do something else. The j times j plus 1 is what you end up with. And so we have to prove that. And the oscillators let us prove that very easily. Here we're seeing that if it's just j equal 1/2, and you square each of these quantities here, and each of these quantities is 1/2 of a sigma, and the sigma is squared to 1. There's the sigma x. For us, that's sigma b. That's the x, and then comes the y, the weird one that was we called c for complex and curly, and then the a, the diagonal one, that's what everyone calls z. So that's the notation that we're using here. And the square of each of these is just a unit matrix. So the 1/2 that's multiplied them, each of them comes out as a 1/4. So you see what we get here, 3/4 for a square of any spin in any particular direction. It's a spin 1/2, so you might say, oh, well, it should just be 1/2 squared, but you can see that it's 3 times bigger than that. And that sort of thing will continue up the road here. And obviously at the classical limit, then the angular momentum squared is j squared. You throw away the noise that the quantum mechanics applies because it's only linear, not quadratic. So we'll talk about that. That's, of course, very interesting if you're fascinated by the boundary between quantum mechanics and classical mechanics. This is one case where we get to see that pretty clearly and without too much effort. And the oscillators help us do that. So here I'm replacing the plus and the s minus with their creation destruction operator equivalents. There's 1, 2, and there's 2, 1 for s plus and s minus, and we do it again here with them reversed. And then sz, of course, is the number operators for 1 and 2 difference, that showing up here. And the 1/2s have all been put at the front end here. A 1/2 squared, actually, because we've got 2 factors. So this is the thing that's going to give us the magnitude of this operator s. We're going to call that j in just a little bit here, but I'll make a fuss about that when it's necessary. The usual commutation relation for these, they do commute if they are not the same dimension, but if they are the same dimension, then you add an extra 1. So that has to be done here. This is normal ordering now. This is a very simple calculation that involves getting the destruction operators, we've colored red sometimes, on the right where they belong, and then the creation operators are hiding on the left. destruction operators are the things that will kill the vacuum, so we get a very reduction in the number of terms we have to worry about. So that's what's going on here, replacing each of these with what turned out to be just number operators. So we've got a bunch of number operators here. So when we apply that set of things to a typical oscillator eigenstate, where you know very well the quantum numbers, then they just simply turned n2 plus 1, so forth, n1 plus 1. So it's just a bunch of numbers. It looks like fairly complicated algebra. And at this point you say, well, how does oscillators led me to? I thought this was a simple result. You put in n1 equal j plus m and n2 equal j minus m, as we've been talking about here, and you end up with this. But it looks like a complicated formula if you look in there and just say, okay, I've got some m's here that they should cancel out, and once you get rid of them, it's pretty simple. You get a very simple result here, j times j plus 1, and that is what we need. So this is something we have to discuss. What's the significance of that little extra j that's added to j squared? The classical part is j squared, and then we got this extra thing that's just proportional to the angular momentum. Now the binomial expansion of this thing, first term, and this is a nearly equals, but it gets closer and closer as we go up, and you'll see you can hardly tell the difference between this one for anything j greater than 2 or so. The j plus a half is, so the sort of the 0-point motion of an oscillator is reflected for the rotor in this extra 1/2 that goes on the angular momentum. If we're talking about the magnitude, that is the square root of the square of an angular momentum j operator. And we will be using pretty soon here j's for everything.
Dr. Hunter?
Yes.
I don't see from that step there, from there to there.
Oh,
From
just
there
go ahead
to
and
there.
do j squared plus j to the 1/2 power, binomial expansion.
Oh.
Okay?
Oh, okay.
Your first guy will be the square root of j squared, and then the product, and the binomial exponent will come down and give you a 1/2. So that's what you get when you expand this and throw away any higher order terms than just the second one in the binomial expansion. Does that make sense?
Yeah.
Okay. Now let's do some geometry. Let's take a look here what these cones look like. And so we're going to have this magnitude of j vectors that is got this little extra quantum thing here. It's 1/2 quanta bigger than the j squared. Okay, so that's what you have. So I have j squared as this, but I'm interested in the magnitude, and that's the square root of j times j plus 1. Okay. So as you go up the ladder here, or down the ladder, actually you start with the highest one, m equal j, and it has the minimum uncertainty. That's really what's going on here. We're going to be imagining a j vector that is everywhere within this cone. That is, everywhere on the rim of the cone, as we'll see. That is what's going to be a pretty good physical picture for what the quantum mechanics is giving us. We've made a wave out of a j vector, and that wave is confined to the bottom or the top of an inverted cone. Okay, and just going up just going down one step here already increases the angle by quite a bit, and again and again and again. And finally, of course, the maximum uncertainty is where the sphere hits the equator. And that is going to be a very powerful way to evaluate some of the quantities we need for high quantum rotors. Anyway, this is a closed form formula for this uncertainty angle for a particular total j, and then the z component is anything from j to minus j. So I shall have a whole beehive of cones here if I wanted to draw it. But I rarely drew that drawing. But it's still what we're dealing with. And here's an example for j equal 30. For j equal 30, we'll show some specters pretty soon again of an SF6 molecule that's going at 30. And the 10.3 degrees is, we need that. The 3 figures, we get a precision of about 3 figures out of just playing with this particular little cone formula here. And you can see for j equals 30, the uncertainty is, you know, pretty big. It's 20 degrees, 20.6 degrees if you count both sides. This is the half angle, okay, the polar angle. And so that particular formula right here is just giving us this. We'll use this in a very beautiful way later on. We're going to use some pretty neat ways just today here. Now this is the biggest uncertainty you can have, j equal a half. So that spinner that we start with has a uncertainty angle of arc cosine of 1 over the square root of 3. Now if you recognize what that angle is, if you have a vector at the 1, 1, 1 direction, okay, you're talking about that angle in a polar coordinate, right? 54.7 to 1, 1, 1. So that is an angle worth keeping in mind. But that's the biggest it gets for spin up or spin down, and there are only 2 states for spin ahead. So we usually don't talk about this, but it's valid there as well to know that. Okay, now let's go ahead and just get this huge collection of matrices, an infinite collection of matrices, a formula for all of the angular momentum J, and then talk about what they do for us. They do a lot of work for us. So what we're doing here is basically we're going to stuff this matrix, if we're going to do this Euler angle, or whatever kind of angles you want to use, we're going to stuff this matrix into basically a binomial expansion. That is what we're dealing with here. We're dealing with creation operators that have had a rotation done to them. That's what this rotation does. It takes the 2 creation operators in order to make the state that obeys this, and takes those and gives a linear combination for the new transform creation operators, A1 prime and A2 prime. Now, I'm using a lot of different notations here for representations, just to, you know, depends on what you're doing, whether you would like to write out the actual terms or else just use symbolic notation with all of the angular momentum. J is written on the exponent, and then 1s and 2s, or actual angular momentum's a half minus a half. I didn't put that one up here because that's so cumbersome. We rarely do that. Or this is a more maybe a telling one that tells that this rotation operator here is having its matrix element evaluated, the 1, 1, the 1, 2, the 2, 1, and the 2, 2, and then this is the compact Dirac notation where the 1 here that has been transformed is given a prime, the 2 that's here is given a prime, and so forth for each of the 4 components. So this is what Dirac would like that. We're actually using this one in this sum right here, and then actually putting the numbers in. Okay, so I just want to make sure you're clear at what it is. This is what's going to be fed into basically a binomial formula that we'll derive. And that's going to be what you would program if you want to program these D matrices. Here's the easiest way to do that. So what we have here, the creation operators primed, and each of those are an expansion like this one. Okay, so I've got a binomial here and I've got a binomial there, and each of them are according to the the way we've done our oscillator, there's the normalization factor there for this would just be a big N here, and this would be an N2 here. It happens to be J plus N and J minus N, actually, where our N we're talking about is a Z component of angular momentum. So those guys, that's where those come from. So we just have to expand this thing. And we're going to fill this space with a little bit of algebra that does that. Okay? It'll be a sum over binomial coefficients. So lots of integer factorials coming into this thing. We already have two of them just as a basic definition, but we need to expand this. And it's good. I've written things a little small here, so you should be looking at the lecture notes when it comes time to do the details of this. All that's happening here is I am replacing each of the things that I get up here, an L and a K summing up. I make that one a J plus M, and then I make what comes out of this guy down here. This is slightly reorganized, and I'm doing a sum over here. I'm letting that one be J minus M equal to whatever came up there. And these are all sums over K. We have to talk about that sum over a K that is making the binomial expansions work for us. So you end up with the J plus and minus M power. And so finally, solving then for the indices that I have here, solving for those and replacing them, so I have just J's and M and N, which are the quantum numbers that we're going to be using for this particular D matrix that's going to come out of this. So here it is expanded a little bit better so you can see what it is we have. This is the general Euler angle representation formula that we will use, and it will give us wave functions and transformation of wave functions for all sorts of different things. Atomic, molecular, and nuclear physics use these things in all kinds of ways, and we'll be taking a good look at some of those ways. Now this sum over K here, it says K seems to go for infinity, so do I have an infinite number of terms? No, far from it. You have a finite number of terms. And the reason for that is it's limited, and I'll show that on the next page here. And let me catch up this lecture here to that page. So here are the formulas that we just did. And then here's the evaluation that we have to do, where this is written up at the top over there. But let me just point something out. And that is, if any of these factorials go negative, do you remember the analytic continuation of the factorial function to the gamma function? And the gamma function has poles at negative integers, right? So if any of these guys go negative, that's an infinity in the denominator. And there's a lot of them if you keep going with K. Obviously, if K gets to be 1,000, it's going to kill anything we're working with, right? So you'll have a negative there. And that will kill that term. You have an infinity in the denominator. That's the way to look at it, I guess. That's best. Now this same thing is showing up as an exponent, you see, in the combinations that we have in the powers there. So this, let's see if I've got this right. When we write it out in terms of the actual matrices, the J plus M minus K right here is that factor there. The N minus M plus K is right there. There's K right there. And this. So any of these powers goes negative, that's not a term you need to worry about. So that's important to see. And that's what you have to put in. And if you're writing a program for this, you have to put in logic for that. Otherwise, you'll be summing to infinity, right? And you don't want to waste time doing that. So that's what we have here. Now, either use the Euler angles, and this is a link that takes you to just see how those related. That's back in lecture 5. I won't bother to take that link right now. But the basic idea, as I say, is prohibiting p factorial, power integer factorial, a minus power integral, which is infinite, in a denominator. So power p must be 0 or greater. So those are the logical steps that you would have to have if you're going to evaluate these matrices in a numerical setting. Okay, for example, d to the 8th, that's a horrendous angular momentum, but we're going to see a lot more than that today. A d8 sub m equal 2, n equal 4, well, it's going to have 5 terms, okay? You go through the logic here and it says that k, my summation index, has to be less than or equal to 10. Well, that's not very much of a limitation. Do I have to sum to 10? No, I don't. Because down the road here, k has to be less than or equal to 4. And then greater than or equal to 0. Okay? Or greater than equal to minus, that doesn't restrict you at all. So these two are the restrictors for this particular case. So this guy right here will just be a sum over 4. So even with big angular momentum, there aren't that many sums usually in the matrix. And this one also will be a sum over 5 terms, actually counting the 0. Okay? And then here's an example where there's just one term. Okay? 8 minus 8, 4. The best I can do there is just sum with 0. That's the only one that I'm less than or equal to 0, and the others are telling me something that's not as restrictive as that. And then you might as well look and see what halves do. Okay, and here again is just one term. Okay, you sum from k equals 0 to 0. It's a single term. All right. Okay, now let's take a look at these things from a point of view of what the waves, what sort of function in alpha, beta, gamma space, and forget about gamma. It's an overall phase most of the time, but let's just take the whole thing for whatever it gives us. And here it is. These there's 2 terms here. You get 1 term here. You got to sum over 2 terms here. So the corner elements have the most summing. The ones in the center here are mostly equal plus or minus, or we'll look at that one last. There are the matrices which then have phases attached by these 2. So this particular one in the center has no gamma at all. It's just alpha. Okay, it's alpha minus sine beta, cosine beta with alpha gone, and then a plus alpha phase right there. Those 3 entities, apart from a square root of pi or something, but they have exactly the right phases for the conventional spherical harmonics, which most people are tortured by. Here they're just given to you basically free. This particular spherical harmonic is equal to the square root of 2j plus 1, in this case 3, over 4 pi times, and you're just replacing here alpha with phi and beta with theta. Remember, they were the polar angles. That was our notational switch when we went to use Euler angles. So that's why it's really good to know about this machine and how the Euler angles are really the polar angles. Beta rhymes with theta, alpha is azimuth, is the key here. And gamma is non-existent at all in this center column. So this is a laboratory description of the wave functions of harmonics that result from just looking at the D function. All of this have the second index here, 0. And we're going to talk very much about what those 2 indices really mean in terms of a laboratory frame and a body frame. That's so key to making this stuff work for us, to take the group theory another step into understanding. So that's definitely a set of complex. These is complex, this is complex. This one right here is the Legendre polynomial for this particular quantum of j equal 1. Now usually when you're talking about j equal 1, you won't use the letter j. Most people prefer to use an L, either an italic one like that, that's most common, or just a plain old Roman English L. And this is the rule. The spherical harmonics for any L and M is just the irreducible representation dl star, and we'll talk more about how it's conjugated. But the value m is the subquantum number for the spherical harmonic. Now usually they aren't written that way, they're written L, m at the bottom. But I want to make a hierarchy of symmetry out of these, so later on we'll be stacking quantum numbers in a way that shows a hierarchy. And certainly you want to write this, anybody that does Wigner functions would stick the total quantum number on the upstairs and let the z component quantum numbers sit in the lower portion. Anyway, this is a closed formula for those. So there are the dipole J wave functions that you work with, and then there's these other wave functions that are sitting off to the side. We have to discuss what those are. Those are molecular wave functions, and we'll get to that in a minute. So one other thing we have to do, there's a lot of white space there, you know some terrible stuff's happening very shortly here, and that is, what I'm going to do is I'm going to write these things in terms of x, y, and z in a complex way, and notice that the middle one is z, but this one is sort of x plus iy, and this is x minus iy. This was actually minus x plus iy. It's called a Condon-Shortley phase convention. All of those phase conventions are taken for automatically by using this formula. So you don't have to argue about why that's minus. This thing gives you minus, it's right. And so this matrix here is going to transform this thing that may be a pretty unfamiliar to you representation of a rotation by alpha, beta, gamma. We got complex numbers for one thing. We need the real one. This will transform us to the real representation that you're familiar with. So that's what we do here. So I take this transformation and apply it fore and aft. I put it here and here. Okay, transposed and conjugated. Okay, and I take this matrix. Forget about the phases for here, but I do keep the alpha, the I alpha. Okay, I do them separately here. This one just produces a rotation matrix that you're familiar with. Now it's maybe a little unfamiliar because you're used to a right-handed rotation, putting a minus right there, and now a minus down here. But remember how those permute through each other. These x, y, and z. Place that in different places. So this is just what you would get if you rotated x into y, y equals x, and had z in the center. All right. Otherwise, you put it back, and the minus comes in the right place you're used to, like this one does. This one transforms the way you're familiar for x and y and z. And that's exactly what I think we're doing right here. This is x, y, z for quantum 1, then it's quantum 0, and then quantum minus 1 down here have those components according to this relation here. So this T matrix transforms this whole thing with the gamma phases into this. And we've seen that before. Okay? So there is the linear polarization x, y, z basis. The other one's a circular polarization basis. Okay? And that's the key difference. Depends on what subgroup chain, as we'll see later on, you're using. Now here's the geometry of just the wave functions that are associated with this. Where the wave function is a cosine, okay? This is the z wave right here, okay? So it does a Thales triangle where the amplitude, you see, and the amplitude squared is the probability. So as I change my angle theta, I get maximum probability to be along that direction. Then it falls back off again, gets shorter and shorter and shorter and shorter, until there's absolutely zero probability of finding some particle. If you're doing some thing where you're counting particles with little counters that are all over the space, the counters on the equator here are not going to register at all. And the ones that are near the equator in angle are going to register very, very slightly, because when you square this thing, it becomes elongated, as you'll see in the next frames or so. And then these guys are the ones that point along the x-axis, and these guys point along the y-axis. And of course, these are the wave functions that do a bonding for a molecule. These are the first wave functions you have available to make overlap that causes a molecule to bind somebody in the neighborhood, say on the z-axis or the x-axis or the y-axis of this coordinate frame. So that's worth talking about, and also the Thales triangle is here. Remember, it's always a right angle inside there, so that is a cosine on the hypotenuse if this is a particular constant d diameter. Now you square those guys for probability distribution, and they cease to be spheres, they become eggs.
Dr. Harter?
That's kind of neat right there. Right?
Can you go back the previous slide?
Sure. This is the...
Yeah, I think there is a mistake.
This one.
Yeah. It's supposed to be a cosine beta. There.
Let's
So
see.
cosine beta, sine beta, sine beta, beta,
Here.
No.
Cosine beta sine.
Yeah.
Thank you. Thank you. Please put that in the notebook. Yes, that's definitely a cosine. Thank you, Lewis. That's very necessary. This one I can recognize is correct. Of course, that's the polar coordinates of the z versus the lab. This one also, you have to worry about the little extra minus sign there. That's because of the body frame that we're going to talk about in a minute. Does that make it? You're clear on that? Okay. Anything else you can think of about this?
Planes. You noticed that you showed how the right triangle there translates into the 3D picture as planes passing through the origin.
Right.
It's brilliant.
And the planes can be anywhere on the azimuth as well. Yeah, that's for sure. No azimuthal dependence of that guy relative to this axis. This is the one we talk about that has an azimuth that we're using. But that's right. One thing I should mention. These two guys get together, x plus, this is x, this is y, this is x, this is y. X plus I times this is what you do to make this one, because this, if I do that, I get a moving wave. Okay? So this is very seldom shown in a textbook. Usually chemistry textbooks will be full of pictures of things like that. Eggs, right? This is what the eggs look like when they're actually in a molecule that has some rotation or a magnetic field turned on or something like that, right? It's a moving wave. You can't stop it. Just when these are degenerate, these two, x and y, they're gonna move. Just the noise will make them move. Well, if you make them move 50-50, you get this. Otherwise, you get some funny little shape here, right? There are a whole bunch of different things I could draw depending on how much of the x and the iy I took. That's the smoothest rotating egg. Scrambled eggs. Okay, right here. All right? But usually they keep the z guy free of that. Right? And these are the two guys that really play the role for magnetic effects, Zeeman effects, all that kind of stuff. Okay, all right, well that's just angular momentum 1. We've got to do angular momentum 2. Okay, that's, we're here, let's do this one now. And that's a pile of wave functions. And what you got to realize is, as an atomic physicist, that's all I'm caring about. Hell with them. But a molecular physicist, I need them all. Okay? That's the truth. And nuclear physicists, too, should be worried about those as well. But in any case, when I take the centered column here and call alpha to phi polar angle azimuth and the beta theta polar angle polar, I am in business. And I have the right phases for everything there. And there were the 5 standing waves that result from these things if I make them into standing waves. And the way I do that is by taking combinations of this guy and this guy, plus that would be a cosine standing wave with respect to the azimuth alpha, And then I take the opposite of that to get the sine standing wave associated with alpha. Then I do the same thing with these two. And if I decide I don't have to do anything with that, that's just a Legendre polynomial straight away. So the center of every D matrix has got a Legendre function sitting dead center. Okay, that's worth noting, and we'll bring those guys forward in a minute. But in any way, the rewriting of these in terms of x and y and z is this. The Legendre polynomial, easy. 2z squared minus x squared minus y squared is what that works out to be. And we're going to go through that when we make a Hamiltonian out of these functions. That's the other purpose of the D function, is to give us a Hamiltonian. So it is very incestuous mathematics here, all kinds of things serving multiple duties. And this guy right here, x squared minus y squared, is an interesting combination that results from taking combinations of these functions in a proper order to make a standing wave. Okay. Now here are a couple of moving wave distributions. This one is not moving. That's the Legendre polynomial by itself. It's all real. The center of the matrix, D. Here's the one that has angular momentum 1, and it makes sort of a flower. And then this one's got angular momentum 2. The centrifugal force is too much. The thing is completely in a plane. They're in a very flat one compared to the angular momentum 1. So those are a couple of things that are neat to mention about these harmonics that are coming out of our D function. Now, always at the center of the matrix, you've got a Legendre wave. And here they all are up to about 4 or 5. Well, 4 right here. And then this one actually is 5. Okay. And the way you get these, if you're thinking of electrostatics, if you're thinking of say, making a dipole out of a positive and negative charge, is that you took the first derivative in the z direction of the monopole. That is, you took the monopole, made a Xerox copy of it, and changed its sign and stuck it just a little tiny bit below or above the original charge. In this case, we're always putting them down lower. Okay? And then I take this thing and I make a Xerox copy of it, put it there, and then take that Xerox copy with a negative sign and put it right there. I get -2 here, and I get a plus hanging down here, and I get a plus hanging up here. The plus here coming from I changed the sign to do the derivative, right? Then if I take this thing, make a Xerox copy of it, and then put that thing down here with a sign changed, this is what I get. Okay? So what you're seeing is you're making a dipole, and then the next derivative makes a quadrupole, and then an octupole distribution forms from the derivative of that, and so forth. Here's a 2 to the 4th pole, there's a 2 to the 5 pole, and so forth. They're all, with their charges, just reproducing Pascal's triangle with some extra minus signs every other diagonal row. Okay? And this charge distribution, which looks kind of unwieldy when you put them all next to each other, but each charge distribution fits in a tiny little space at the origin of this, and that's the wave it broadcasts. So this is some, this is kind of neat to realize that a little, I take this thing and infinitesimal it, make it very small, okay, if we're actually doing it in some experiment in a lab with charges, and I put that, and that's the distribution of potential that you would see, electrostatic potential that you would see. Kind of neat, huh? You can see the thing, making the little pieces, each of these, that come from this guy here and this guy down here, we say. So that's kind of neat. So this is Legendre's cylindrical symmetry. They all have cylindrical symmetry because the M is 0.
Dr. Hunter,
This M is 0.
could you once again tell me, please, how you construct this Pascal's triangle? Like how you build the
How I made this
how
out of
how
this.
you, yeah, the multipoles, yeah.
Let me remind you of something I think that you've already seen in chapter 10 of the mechanics, where we just did complex variables. We just did dipoles in a plane, right? So I took a monopole, which was 1 over z, right? And then I take 1 over z plus delta and minus delta to balance it, okay? Subtracting those two from each other, right? And I got the dipole wave function. The monopole wave function, which is just a thing like this, became a dipole wave that went like that very easily. And that was just taking the derivative with respect to z. Now that's the derivative with respect to x and y, right? Okay, this is the derivative of x, y, and z, whichever direction you want to go, right? So that's basically what a derivative means. It's f of x plus delta x minus f of x, right? And then you scale it with inverse delta x, right? Which makes, these very close together, right? So that I can then stick them at the origin and get that. Does that make it a little clearer what is
Oh no,
going
like
on
I
here?
was wondering like how you put those -2, -3,
Well-
-4, +6.
Let's do this one,
Yeah,
okay?
There's a foot
So I
above.
make a copy of this one, right?
yeah.
Put it here. Then I take the Xerox copy and change its sign so that this was positive before, it's now negative, so the two negatives see each other, right? Does that make sense? And then I had a negative down here before, but I changed the sign to positive. So there are the two copies. Negative, negative go together here. Positive and positive are at the ends. Does that make sense? Now it's a little hard to take this with 3 fingers, but you can see the first one's right. You see? And then I'm going to take my 3 fingers with the signs changed to make that. Okay, that's a hand-waving proof of Pascal's triangle by charges, right? Pretty soon I run out of fingers, but okay, I run out of hands, which is what I run out of. Yeah. Okay, so that's a neat piece of physics that lies inside these functions. Okay, and there's more. We've got to do some more.
How the shape of so for example like the last one, like where you have like +1, -5, +10, -10, +5 and -1. What if I
Matching
have
each of those.
if I have like for example like I don't know like thousand terms there would like I'm interested how that would
It's
change
just a
the
flower.
it will just stack
Yep.
shut like
It
will
gets
just go-
narrower and narrow on the first one, right?
Okay.
And then there's room for even narrower cone here, and then another one, another one, another one. And finally, there's the one that goes with 0.
But what would my interested? I'm interested in like what would happen like to the charges piled up at those center.
Even these
points.
guys.
Yeah, it would be a lot of charge, right?
And a lot in the center. Yeah, it gets the numbers in the center go up, rapidly. That's right. But to make these perfect multiples, that's what you need. That's what you need to get it. Now remember, for the wave functions, these guys here represent phase. Okay? I mean, the dipole right here, that means this guy is out of phase with this guy. Okay? And when you think of a wave function that's, in an eigenstate, where the phase is positive and negative, that's the antisymmetric eigenstate. That doesn't mean that you have an electric dipole that has plus and minus making a dipole field. And to get that, you need to add this guy to the wave function where it's symmetric, a monopole-like structure. When you add that, then you get something oscillating a dipole. That's the way atoms radiate. We've talked a little bit about this. We had the two wells, and we made a wave function that was symmetric, and then we made a wave function that's anti-symmetric. We added those two, and it all piled up on one side. But then if they get out of phase, it piles up on the other side, and then comes back and piles up on the original side. And as it oscillates to the beat frequency. Remember that stuff? Okay? So don't make the mistake that I think a lot of people can graduate with a PhD and make that mistake of thinking just because I have a wave function of plus and minus phase that I've got a dipole electrostatically. I do not. There's equal probability of charge on both sides. It's just their phase is different.
I see.
Now you add this guy to a symmetric thing, now you got a dipole. It takes two to tango in quantum mechanics. You don't move if you're just one eigenstate. Only your heart beats and no one can see that. It's mortal.
You can get it to any symmetric wave function and you will still get a dipole, right?
You take any combination of these two, you got motion.
Okay.
Yeah, any combination. And remember when we did the demo, all it took was a tiny little bit of one of them to make it move, right? A lot. That's why we're getting to see the green here, right? The very tiny amount of difference on your rhodopsin molecules that are giving you your eyesight. Very tiny, very tiny. And very tiny excitation of the cobalt or whatever it is in the tungsten that makes the bulb shine. Very tiny. Okay. Lasers are amazing because they do 50-50 and more. Rabi oscillation, right? That involves 100%, and then 0, and then 50% population reversal. Right? That's what you need to get really a lot of laser light. But finally, when you get top, it stops broadcasting, right? When you get to the top, you're in excited state. No more broadcasting. Okay, these are little points that worth mulling around because it opens your horizons of understanding to this. Now I've got something that really, it's right in the middle of the lecture here, is mind-bending. I really need to do this in order to make the molecular wave functions work for me. The atomic wave function, I don't need this, but for moleculars, I got to talk about Mach. Now you remember the Mach principle? The idea that if I have a bucket of water, this is one they always use. Newton was, I think, responsible for thinking of that. And the idea is that if you take a bucket of water and rotate it real fast, the water inside makes a nice parabola if you're doing it nice and evenly, but finally it overflows, right? And the water flies out. Or you just take a pan and rotate it this way, the water flies off, okay? Or you just take a dog and shake, right? Water flies off, right? Okay. Mach wondered if I could have the dog or the pan of water sit still and shake or rotate the rest of the universe. He says, that would cause the water to fly off if you did that. This was his thinking that there's some kind of weird relativity associated with rotation. So Mach's principle was that, yeah, in order to make sense of Newton effects, the gravitational effects, he needed that. Now, most people make fun of this. I'm doing it right here. I'm calling it the Mach principle. But we're going to be very, very precise about this for a number of things. In particular, just plain old rotations is where I need to do it. Because what we're going to do here is make molecular wave functions out of the D functions. But to do that and make it work for us, we need to talk about what we are having as far as rotational relativity. So when I wrote this Reviews of Modern Physics so long ago, I used a picture like this. I said, we're all used to having something that rotates, and then we have tools, a suction cup and a crank, or this Euler machine here that goes in, and it turns that thing, and we define Euler angles accordingly. But to really finish the description, I need to possibility that the thing that rotates could do it itself. That is, it could have little cranks that reached out to the surrounding sphere, grabbed onto it, turned it there, and then pulled the crank, and then put it down somewhere else. Now it'd be here, and it would rotate around that axis. So basically having an Euler angle machine that worked from the inside as well as the outside was essential to the logic of what we're doing here. So we needed to have a set of operators that we're used to, that work in the laboratory and do rotations, R and S, depending on, you know, where you put your crank. You could have one crank that you move around just like we do here. But we also need to have that ability, at least to think, about the object itself, thinking that it's moving the entire universe. The universe is represented by this sphere. I mean, if they do it slowly, they won't be able to tell the difference between the case where they actually had a nice light sphere here and they just moved it around. So there are two things here that are getting rotated that are independent of each other. And the idea is that I can use the standard laboratory operators on an initial state and produce some new state, call it the R state, but I will get the same relative position of those two things if they do the work, and they have to do it inversely to what I did. So each operation here corresponds to an inverse operation by the inside jobs. So the body operators, the ones that have little bars on top of them, have to commute with every one of these. With themselves, they don't commute, mostly. But with the others, they do, because these are independent. I can have them set their ball, and then I can come in and apply an operator that resets it. I could do those independently. They are independent. So I could do one of these or two of these first, and then have them do something, and then come back and do this one second. Or I could do in a different order. I could do the second one first. They could act first, or I could act. The same result. You're going to get the same result with these two independent rotations. So this is something that's really this extrinsic operators versus intrinsic. We will talk more about that with respect to finite groups, but it's true for this infinite group. Archimedes said, "Give me a place to stand. Otherwise, I can't move the earth." Okay, that's the Archimedean thing between the Mach Principle. That you have a relativity between rotations of different things. So here's the picture that we're going to have of the D functions that have an M and an N subscript. Those D functions, those wave functions, represent, with the M, the Z component that you're used to. And that's all you need if you're talking about a single particle or a diatomic molecule. We'll talk about that a little bit more in the next lecture to clarify that. But the M is mostly what you see in the textbooks. The textbooks of quantum mechanics of rotation say, I got an M, it's a Z component. But there's another component here that represents what the whoever it might be that lives on this molecule is flopping around, and this molecule is flopping around the J axis. The J you see in the laboratory is a conserved quantity. This does not move. I don't get a Hamiltonian to move it from the outside, but there is a Hamiltonian of this molecule
that's going to move it with respect to the laboratory. The question is, what do somebody on board that molecule see? And it will see the J vector going around on some angular momentum cones that we have. So while the J vector in the quantum mechanical system is not totally conserved, it only has a Z component that's conserved, the X and the Y components are uncertain. These are uncertainty cones that I'm drawing here. And that J will be anywhere from here to here, and then according to the body thing, depending on their value of N, and they'll maintain that component, that will be conserved just like this one is. So they'll see it anywhere from this side to that side, and then this whole thing will be anywhere in the laboratory. So that's what we're dealing with here. That's what this rotor state with M and N, we're attempting to picture it. And boy, is that hard, because things don't act like that in the classical world. So, what we have to do is just take a look at the projector that produces a state that uses the wave function dJmn. So basically what's happening here is I'm considering all possible alpha and beta and gamma of this rotor. And I mean, if this were a quantum mechanical object sitting here on the desk, it would be in all of these different positions in lesser or greater degree, depending on what the amplitude of that particular D function was at a setting alpha, beta, and gamma. And we're going to sum over every one of those. That's the crazy thing about this state, is it's a sum over all the Euler angles of a vacuum state. Rotations of an initial thing where it was at whatever you call origin of the rotational space. So I'm going to be summing over every one of these guys with some kind of metric, okay? And if there's anything else I can say here, there is a number here that serves as a part of the normalization. That is just 2j plus 1. That's the dimension of the space that these wave functions have. And how many n values do you have? You have everything from j to minus j. That's 2j plus 1. How many m values do you have? Same thing. Well, that quantity there, something we will worry about much more carefully later on. But right now, if you have an integral j, 0, 1, 2, then that integral is just over beta from 0 to pi. The asmias, both internal and external, go over 2 pi. Now when you get done with this integral, the 8 pi squared cancels everything, but what I want to do is get a count of the number of states that you're talking about. So this thing will be normed by the number of states for reasons that come up much later. So I'm just getting it in there now so I don't have to stuff it in later. So that's what this integral is, okay? Now, if it's fermion, it's not both, those are bosons or classical. If it's Fermi, you got double this. You got to go from minus pi to pi with the beta. That will cover the double space that you have to account for with the Euler angles. So there's a little screwy here. This is more of that 2 to 1 business between the angular momentum, that's its half integral, and that which is integral. Jose Fermi. Okay. All right. So what we need here, and this next thing here, is we need to see how these things transform. In other words, these are going to be the wave functions. These are the amplitudes to be at a certain position, alpha, beta, and gamma, which is what a molecule can do very easily. So that's what we're working with here. That's the state that we're working with, sort of pictured as best I can at this particular a time. But I'm going to try to fill in that picture with all this stuff, because it's the uncertainty cones that determine where these waves go. So, the first thing I want to look at is a transformation matrix. Now, I'm going to apply an R to this crazy state. Now, this is an R that lives in the laboratory, so it's only going to affect that M. And there's going to be a sum over that M prime, from j to minus j. That's 2j plus 1 terms in this sum, with each of these different functions, alpha, beta, and gamma, that are indexed by the M prime. And we'll keep the M constant, because that's what I started with. I'm sorry, we'll keep the N constant, that's what we started with. That does not change. And I get a combination here when I do this transformation that just involves the M's, just involves the M's. So spherical harmonics don't know about the N. And as I said, N is equal to 0 in that case, but there are other wave functions awaiting here that have non-zero N, and we need to recognize that. But here's the Mach principle. The Mach principle simply says that the rotation that we're used to, that we use in a laboratory, that gives us alpha, beta, gamma position state, is equal to the inverse of the body's operator, alpha, beta, gamma, operating on the same state. And furthermore, those two operators, no matter what value of angles for this one and what values of this one, doesn't matter, they all commute. They all can be flipped. And they're equal in either order. So that's the Mach principle right there. This one and this one. Now, that does not mean that R is the inverse of R bar. It only means that the effect of this on the one vacuum, couple vacuum state if you like, the effect is the same as this and the inverse of the bar operator. Nevertheless, we do get two transformation rules here. This one is the R making a sum over the M's. This one is R bar making a sum over the N's. Now the way to see that in direct notation is this. Here is the matrix element M prime M for the laboratory operator. It is the D function M prime M of that particular rotation, alpha, beta, gamma. Now, let's let the body do its thing. Imaginary, of course, but if it does it, we'll have a matrix element just like that one, except the N's are involved, and they're the ones that change. The M is not affected. Moreover, this will be 0 if there are unequal N's. In other words, if this N isn't equal to that N, 0 is what you get for this. And that's part of this Mach principle. And over here, if the M's are, they have to be equal in order for us to get a non-zero result, which would be the same function, dj, but now involving N's, the N values in place there. Okay, I think it helps to have some pictures of this stuff. We can do all the rotations, and we can do all of the generators. Now this is important, the Z component, J, that generates the alphas and gamma matrices here, sees this vector as an eigenvector with the M value. The other operator, the one with a bar on top of it, measures off of the Z bar axis, which is wherever that body happens to be, it's going to be seeing minus the N. That minus there, simply because if I reach and do a counterclockwise rotation myself, in order to get that, the body people would have to see it as doing a clockwise rotation of me. So I end up in the same position relative to the to the body, or the relativity is correct. Absolute value doesn't matter. That's the Mach principle, because we don't care. Only the quantum mechanics is only really caring about the interference between this thing and this thing, the inside and the outside, if you will. Okay, so this is just reminding us of that. Okay, this M value here is what's of interest to operators that we are used to. Most atomic physicists and physicists in general are fully aware, and this thing is just isn't there as far as in their world. But if it's a molecule, you've got to have it, you see, and you've got to have the operators that go with it. All these R bars, and you're going to have S bars or J bars, and I should probably point out at this point, henceforward, we're going to be using J or J bar instead of the S or S bar. Okay, so that's going to happen right now. But this is just summing up the stuff that we're dealing with. Now we have to look at what it really happens when you do a transformation. Okay. Now this is the simplest case. Most people are familiar with this. This is called generalized Stern-Gerlach molecular beam experiment. The idea is that you have some kind of device like Feynman uses in his book to do virtually all the first parts of quantum mechanics as some sort of filtering mechanism, which is just be a non-uniform magnetic field, and they're sending in something that has a magnetic moment and a magnetic momentum to go with it, and it will separate, say, an angular momentum 2, total 2 state that's, say, pointing straight up or anywhere into a bunch of possible states coming out here with different angular momentums relative to this axis. And so the question here is, suppose a spin J state, and I mean one that's got an n component of 1, and that's with respect to this particular analyzer right here. Okay, so this state right here is the rotation by beta of one of these states. Okay, and this particular one is being attacked by the rotation operator to make that, or the filter here has put out a state that is oriented with angular momentum 1 on this tipped axis here, tipped by, say, 15 degrees or so. That's what it looks like. Okay, so suppose a spin J state, in this case J equal 2, and N equal 1 has been rotated, and it exits an analyzer. That's what this thing right here means, is it means something that has a rotation beta. Okay, so it comes out, and then it gets to enter a vertical, perfectly beta equals 0 analyzer, and is forced to choose, as Feynman likes to say, from each of these blue states here, these unrotated states, J to M prime. Okay, I'm using color M prime for the left-hand final index and the green color for the initial thing. So we're going to be looking at all the D functions, you see, associated with something that came in as 1 and then was forced to maybe choose 2, 1, 0, -1, or -2. So a certain amount of states are going to come out of here. I'm imagining a pretty large number, and then a very large number here, because beta is pretty close to 0, and then a smaller number here, and an even smaller number here, and a very minuscule number down here. So we're really looking here at a Stern-Gerlach experiment, but not with spin 1/2, spin 2. Okay, we're looking at roughly 4 times as many components. Or let's just say we're, I'm thinking of 2 as being 4 times 1/2, but you know, cut me a little slack on that sort of thing. But the idea is that you get, using these functions, the prediction of what you'll get at each value beta, okay? If beta is pretty small, like here, well, you can see there's practically nothing coming out in the -2 channel, and next to nothing coming out of the -1 channel. And out of the 0 channel, we're starting to see some activity, pretty good activity right there, because the next one is virtually 100%, okay, in this neighborhood. And then this one better be 0. So they all better be 0, except for the one that it's, you know, was born in, all right? And that's this guy right here, okay? But as you move out, pretty soon all of them get to participate more or less at once, until you get so you've turned the thing completely over. If you've turned the thing completely over, then all of them are 0 except for -1, right? Because you turn 1 over, it's -1 now. So you expect that to happen. It does happen. Now, remember, when we do the square of this thing, the phases get killed. So all of these reds are above 0 or on the positive side of the axis. The things that actually show the value of D are the turquoise curves. Okay, they keep the phase for exposure. All right. Okay, so how can we get our minds around this? This is just presented the way it's usually presented. It's a mystery. Don't worry about it. Shut up and compute. That's the David Merman, I think, is credited with saying that. Okay, it says, we don't know. Just shut up and compute. Right? Well, I didn't go for that, and that's what I want to show you. Is a way to look at this thing. Now, here's a picture of the whole possibility where I start with all of these are starting with n equal 2, then there's actually -2, and then there's n equal -1, the initial state, 0, okay, it's pretty neat. So this is the whole D matrix plotted out. And then these things are here, we're going to talk about those later. That's the actual molecule showing these things as a wave function, because it's doing this experiment on itself as it rotates. Okay, so basically we're looking at the overlap of the state, say 2-1, on a unrotated state, this thing right here, on unrotated beam analyzer corresponding to D matrix element, this one right here. So that's what you get if you plot them all. Okay, still a mystery. What the heck's going on here? Is there any way that I can see what in the heck happened? This is just doing it with our new thing. This is something you can set up and run. We'll show some things here. But here's where I actually go ahead and use a pretty high angular momentum, J equal 20. That's 2 times 20 plus 1. 41 possible states. Okay, so we're going to look at what it is that happens if I put the narrowest cone or the next narrowest cone through an analyzer that is not rotated. These are the count registers for an analyzer that hasn't been rotated. This one has been considerably rotated here, a beta of 45 or 46 degrees, okay? Or a beta that's all the way up to 90 degrees almost, okay? And here's what you see is a plot of this D function for D20 as a function of beta equal 85 or beta equal 45, okay? But mainly as a function of M. So this plot right here is the plot for a fixed beta, fixed J, of course, and fixed M versus M prime. Okay, final state M prime. That's all of these. It started out at 2020, that is, this is 20, n equal 20 on the axis of whatever it is that has this angular momentum, whatever the chosen axis is. It gives you sharp 20, okay? And then it's going to be able to choose all of these guys. And these guys down here too, okay? But you can see very obviously that when you draw it this way, you pretty much are confined to the edges of this cone. So if you're thinking of a J vector, trying to get your classical mind to work a little bit, that's flopping around on the tip is going around the rim of this cone right here. So back and forth it goes, very high probability and amplitude, probability amplitude, that's what the green thing is, or probability, that's the red thing, okay, that's the psi star psi, this is the psi equal to d, the d function, this d function right here. Does that help? And you can see it's making sense. But what's really mysterious about it, particularly when you get really high angles, is it's producing a wave function that looks very much like the vacuum 0-point oscillator function. And here's the next one up. A pseudo-oscillator. And you got to remember, every one of these dots is a completely different function. At least, if you just look at it, you get completely different combinations of sines and cosines. Every one of those dots is a completely different combination of sines and cosines given by this function. Remember, it's a matrix full of polynomials, right? So this is what what we're faced with. It's really quite a remarkable thing. I'm going to go ahead and bring this guy up to speed here, and we'll try running some animations just to give you a feeling for what it is you can do yourself when you play with these things. I'm going to go ahead and see if I can get, I think this one is one that visualizes this particular sort of, there we go, okay? And what you can do with this thing is you can change the angle. You raise the angle if you click on this side of the equal sign, okay? So I can raise the angle, just, you know, a lot or a little using that. But what's really fun is to leave the j equal 20 alone at first, maybe bring this one down. If I click here, nothing happens, but if I click on this side of the equal sign, I come down to 19. If I click again, I come down to 18. And then go back here and take the angle either up. Now if I take it up and go too far, like if I can get this this cone to lay over on the side there, you'll see very briefly there, let me bring it back, that you have a lot of confusion right at the, see if I can bring it, I think I want to go a little bit more. Here we go. Look at how all the dots, except for the 19th, are 0 or near 0. See that? There's one dot over 19. And then, as I bring this thing up or down, depends on which way you're going here. There we go. We'll bring it back. Okay. There's where 19 was the only one. Then it starts to reorganize. Looks chaotic at first. I gotta go. Here we go. Okay. And as I pull this thing more and more toward the center, this pseudo function, the pseudo oscillator function, right about there is the center, pretty close, 80.8, 81, 90 coming up here. Okay, there it is. Oscillator function number 2. This is 18, actually not 19, that was having the magic behavior. Okay? You see what this crazy thing is doing? It's really amazing. I click it down, I keep getting more and more oscillator functions. I click it up, there's the, just above vacuum state, and there's the vacuum state. When you think of oscillator, right? Isn't that something? Bizarre. The bizarro world of quantum. Very much bizarro. Okay? Here's a whole, you can get a whole table if you want to, of these things, just so you can see. As I take this one off of 1,0,0,0,0, which is just your thought or normality, even the smallest angle, they start to rise a little bit. But they only rise underneath the cone edge. This will draw the little cone edge, and you can see there's an inflection point. The inflection point for this curve, as though you were going from the classical region to the non-classical region, it's right there. It stops being curving this way, flattens out, and curves this way on the other side of this line.
Schrodinger behavior, right? In a oscillator potential.
Isn't that weird? Oh, that's very weird. Okay? So all of these are clickable. You get the whole table at once. Here's 30, which is what we looked at when we first mentioned these angular momentum cones. Doesn't go away just because you use a high angular momentum. Okay. Now, here's some quick analysis. The thing is, we're going to use this as a quantitative tool. And here's the simplest thing you would do. Figure out where the most busy counters are and what's the probable values. You can just go ahead and do some trigonometry with the cones, figure out how big this thing is, and then see what its projection is. And if you do that, you get a pretty good answer for what the width, the delta M, the uncertainty width, where those two lines connect. Talking about these two classical turning points, if you will. But this is all quantum mechanics. There's no things about classical here. Okay, and then you can go ahead and go for higher values, lower values, the ones that have more uncertainty. And then you can start asking, what in the world is the probability that I would see this axis here that's flopping around for a particular state with a value m and n fixed, okay? And then you see some really crazy stuff, okay? And this is something that you should to play with on your own time. And I have to admit there are a lot of things about this that I have not figured out yet. I mean, it is really quite remarkable, a bunch of things. Again, you click on this side here, and you make the m value go down, okay? And then you click on this one, same thing, make that go down. You start getting a lot of very wide cones who meet each other at a certain place. And when that happens, there's wave function everywhere. But as you make this thing, say, 0 and go through to the other side, it starts to open up regions where there's very low probability. Again, the probability is red. The probability is green. The probability is red. The amplitude, the actual D function, is green. Okay, so there's again, now the cones are actually being projected onto a circle, a sphere, if you will. Okay, so these are the D functions as wave functions of a rotor. The rotor indicated by two atoms that are flopping about, and that means it's flopping about this cone, and then that is rolling around this cone. And those are the two minimum uncertainty cones right there, because I've got 20, 20 for angular momentum, total 20. Okay. Well, we still got a little bit of work to do here before we're finished, because I would like to start the next class with the other use, the fourth use of the D function, and that is to produce a Hamiltonian. So, as I said, this quantum mechanics is very incestuous. You serve as cousin, second cousin, and uncle of the same people in the family, no problem. This is very, very southern. So, get used to a lot of efficiency, right? It's a lot of efficiency. You don't need to go to the store to get something new to do each one of these tasks. You've already got it. It's this darn D function. It does all the work for you, quite literally. So the deal here is I'm going to make a quadratic Hamiltonian, and to do that, I'm going to use quadruple functions. Okay, things that are quadratic in this Cartesian components. And that is not hard, it's just tedious. You have to write out each one of these functions as x, y, and z. Okay, because I'm going to make a Hamiltonian out of jx, jy, and jz. Not too different from what we've been doing when we did the ABC expansion, except now it's, there's an infinite number of different kinds of expansions that you can do. So the deal here is that the x, y, z polynomials will become rotor tensor operators. Okay, and we're going to be using J instead of S to accomplish this thing. So basically this is the, and these are called, these sometimes have a name when they're written as x, y, and z. They're called the x functions. Okay, they're multiple functions is a full name. Okay, x functions is what I call them. But they're just D functions. With the kth power of the radius. If you talk about angular momentum k, total angular momentum k, which we will let the integer j describe. Well, k is what you use when you're making an operator out of the thing. So the high index here is the total, okay. The rank of the tensor is what we're talking about if you think of these things as tensor operators. And this is a quadruple operator in angular momentum. That's the thing that's really weird. You see, you can make one for a potential, but we want the kinetic part, the rotational part. So we're making a Hamiltonian of an asymmetric rotor. And that's what we're going to be talking about a lot in the next lecture. And anyway, let's just go through the basic algebra. That's 2, 2 right there. So I've got x squared and y squared that I have to play with. And so I make an expression like that. So these are, and you can keep going all the way down to t0, 0, which is just the sum of the squares of j. Okay. And we use that one first, and then we use these guys.
So
Yeah.
here you're just denoting it as, the T stands for tensor of rank 0, right? That's what the T00 stands for.
Except that I always have the same power of j, x, y, and z, right? Total power is always 2 for this particular game here. So, in a sense, they're all rank 2, because the diagonal tensor would be called rank 2, right? X, x, y, y, and z, z. Does that make sense? Okay, so here's what they look like. Now, I should point out the polar vector, dipole vector, okay, lacks inversion symmetry. It goes minus when you invert it. And that means, because we're talking about angular momentum, it also breaks time reversal symmetry. So we don't use this one to start with here. That would be if I put some gyroscopes, gyro rotors I call them, rotors that have something that can couple to rotation or magnetic field. Then we would add those guys, those 3 guys. But we're just going to be stuck with this guy and this guy in what we're doing here. Okay, and the monopole. The monopole is the one with rank 0. Okay, so we'll do rank 0 and rank 2. That's all we're going to work with. Now we leave out what we call the T2 tensors, the YZ, the XZ, and the XY. If you use a diagonal if you're in the body frame, your Hamiltonian is diagonal. And I don't have any of those. So the products of Jx, Jy, Jx, Jz, Jy, Jz, not going to have any of that if I've got a diagonal tensor. So that really simplifies the thing. I guess so I only have to work with this guy, and then that guy. So there are three guys that I'm going to have to work with here for this rotor, in order to take care of the three parameters, A, B, and C. Okay? So this is the kind of machinations you have to go through to get the angular momentum power to work for you on stuff that you normally wouldn't think you'd need to use it. So this is all just going to be writing these things out very carefully, just to make sure that I have the right coefficients. I've separated the thing into something that would be the only thing if A and B and C were all equal, those guys would be out of here, okay? And the very last one, I call the asymmetry term, because that one would go to 0 if I made A equal to B, and that's what we're going to work with first in the next lecture. But right now, I'd just like to show you a picture of what you get from looking at that one, okay, without asymmetry. So now you C minus B, that's being held constant here for the Hamiltonian, and then we vary it to see how that affects. Here is the picture of that thing, okay, that Hamiltonian, written just like this. So as cosine squared of theta. This is just something going as cosine squared of theta, okay, plus a constant, okay? So it starts out, and cosine starts out at 1, and then drops to 0, okay? Well, there's 0 for the cosine, but there is that value right there as radius, okay? So we're measuring radius here as the actual value of this Hamiltonian as a function of the angle theta. And then I'm putting all the angular momentum cones that go with angular momentum 10 in there. And what you're getting is that that's the actual energy of the 8 state for this particular Hamiltonian in angular momentum 10. So what we're getting is something that's really quite remarkable. But you can sort of see here that this J plus a half is pretty close to 10.5. It's actually supposed to be 10.488, but that, you know, that's within 1 decimal of 10.5. So you can see that this top of the cone here is only just a little bit, this thing right here is just a little bit below a half of that distance between the quanta. So this is 1 quanta, there's a half a quanta right there that this thing starts its value at the highest value, 10, of Z component. Okay, and then these uncertainty angles that we talked about are exactly the angles that these things. So you substitute that uncertainty angle into this, and you get, and this is what's so really surprising, you get the correct value for the thing. Here this gives this uncertainty theory, okay, gives exact quantum eigenvalues for a symmetric rotor. And we'll end the lecture with that, but I'll just show you what's coming. When it's asymmetric, it's an approximation. And not a very good one for something that's totally asymmetric like this. So we need to see, what do we do with things like that? That'll be the next topic. And we'll also have another way to look at the original problem, which is the symmetric rotors. Okay? So we're finishing not too much over time, but if you have any questions, please bring them up now or in private later or whatever. Okay. Well, you have your thing, your meeting?
Wednesday, so I will send the
Wednesday.
Wednesday, not today. Wednesday 2 to